Hello everyone, in this video clip we are talking about the last section of this chapter, that is the Graham-Schmidt process. Okay, before we talking about what is the Graham-Schmidt process, so so we need to review something to you. In the section 2 we are talking about the orthogonality in the vector space, right? What does it mean? It means if we have a vector, two vectors, it's not a non-zero vector, u and v. We said that u and v are orthogonal if and only if the inner product of u and v is equal to 0, right? Okay, and sure, we can define the orthogonality in any inner product space. Okay, so if if you can remember the topic in chapter 2, so we said about we said something about the basis, right? So we know that in R3 we have we know that the dimension of the R3 is equal to 3, right? What does it mean? It means that if we find the basis, so the number of the element in this basis is 3. Okay, so and you can see that the one basis for R3, I mean the easiest, you can find the easy one or the simple one of the basis of R3 is this one, right? It's the standard inner product. Okay, and if you draw the vector, if you draw three vector here, so 1 0 0 is like here, 0 1 0 is like here, and 0 0 1 is like here. You can see that three vectors are orthogonal, right? And if and you know that if two vectors is if three vectors are orthogonal, so so maybe if we can find or we can do something easier. Okay, so our question is, if we have a basis, okay, if we have a vector space V, so we know that it has a basis. Our question is, can we find a basis such that this basis is orthogonal? Okay, so we will define about what does it mean of the what does it mean of what is mean of the orthogonal set. Okay, so this is what it will lead to this definition. We say that if we have a set, if we have a set with two or more elements in the real vector space, we say that we say that the set is orthogonal if all pairs of distinct vectors in that set are orthogonal. Okay, so this is the meaning of orthogonal set. Okay, and if that set, I mean if the orthogonal set has the norm 1, I mean each vector in orthogonal set has norm equal to 1. Okay, we said that that orthogonal set is orthonormal set. Okay, so the difference between orthogonal and orthonormal set is orthogonal and add condition that each vector has norm equal to 1. Okay, so if we write down as the math symbol here, so if we let S be a subset of a vector space V, okay, and F has the element less than, greater or equal to 2, and 0 is not the element in S. Okay, so we can define that S is orthogonal if and only if for every vector u and v in S, u dot u integral with v is equal to 0. Okay. Oh, sorry. Okay, yeah. U integral will be equal to 0. So this one is hold with the condition that u is not equal to v. Okay. And S is orthonormal set. Okay. If and only if S is orthogonal and at the addition that the norm of u is equal to 1 for all at u in set S. Okay, so how to find norm? So the norm of the vector is the square root of the inner product of u and u. Okay. Okay, so this is the definition of the orthogonal set and orthonormal set. Okay, so we will move to the example of the orthogonal set and orthonormal set. Okay, so the first one we focus on R3. Okay, and we let V1 be the vector 0 1 0, V2 is the 1 0 1, and V3 is 1 0 and minus 1. Okay, and we use the Euclidean inner product. Okay, so it's easy to show that if we calculate the inner product of v1 and v2, v1 and v3, and v2 and v3, so the value of all are equal to 0, right? It's very easy to calculate it. So this set is orthogonal set. Okay, but for this from this example, so I can ask something here. So if this set is the set of v1, v2, and v3 orthonormal, the answer is no. Right? Why? Because if you calculate the norm of the v1, okay, so the norm of v1 is equal to 1, right? But norm of v2, this one, is equal to the square root 2. It's not equal to 1. Okay, so that's why this set is not orthogonal set. Okay, but I think you can see that we can change this set. We can change this set to orthonormal set, right? So how to change it? How to change this set? How to change this set to orthonormal set? We know that this one is orthogonal, right? But it's not orthonormal because the norm of the vector v2 is not equal to 0. It's not equal to 1. So how to change this set to be an orthonormal set? The answer is very easy. So if you need an orthonormal set, so you need to normalize it. I mean, you need to normalize each vector. What does it mean, normalize? Normalize is mean you make that vector to be you make that vector to be a unit vector. So how? Yeah, so we will use the norm of that vector by divide the norm of that vector into that vector. Okay, so from this one we know that if we find the v3 here, so the v3, the norm of v3 is the square root 2. Okay, so if we use the norm of v1 and divide by the v1 and v2 divided by the norm of v2 and v3 divided by the norm of v3, so this one is equal to 0 1 0 and 1 square root 2 or 1 over square root 2, 0 and 1 over square root 2, and the third one is 1 square over square root 2, 0 and minus 1 over square root 2, like this. And you can see that the new set that we obtain is orthonormal set, right? Okay, so from the I think from this example you can see that it is suffice to find the orthogonal set, right? Because if we have a orthogonal set or yeah, we have a orthogonal set, you can find the orthonormal one. Okay, so this is so that is I talking before. Okay, here. Okay, it's not hard to find. Okay, but so now we are talking about the basis, right? And if we need to check that, if we have a set, so we claim that set is a basis for some vector space. So one thing that you must do is you need to check that S is linearly independent, right? Okay, but now we have the definition of the orthogonal set. Okay, so from this theorem, it's tell that if you have the orthogonal set of non-zero vectors, then S is linearly independent. What does it mean? It means that if you need to check that set is linearly independent or not. If that set is orthogonal set, so it implies that S is linearly independent. Okay, and from this one, I think the method to check that the set F is orthogonal set and the method to check that F is linearly independent set, I think the first one is easier than the second one. Okay, so how to prove it? The proof is very easy. Why? Because we know that S is orthogonal set. What does it mean? It means that if we have the inner product of v1 and vj, and if j and the inner product of vi and vj, if I equal to j is equal to the norm of vi square, right? But and the norm of vi square is not equal to 0. Why? Because the element of S is not equal to 0 vector. Okay, and the inner product of vi and vj equal to 0 if I is not equal to j, and this one is true for all I and j in the set of 1 to n, right? Because we have n vector. Okay, how to prove that S is linearly independent? Yeah, we use the definition for the linearly independent. So we assume that if we let C1 to Cn be the scalar or be the real numbers, then such that C1 V1 plus blah 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 to Cn Vn and equal to 0 vector here. Okay, so we need to show that C1 to blah blah to Cn are equal to 0. So how? So you need to calculate, right? But this one is very easy because S is orthogonal set. So we will use the inner product to help us to find the value of the value of C1 to Cn. Okay, so how? So we will use the inner product. Okay, so we take inner product from both sides. Okay, and we take inner product with Vi. Okay, so this equation so we inner product with the Vi in the left hand side and the in the left hand side and right hand side. Okay, on the both sides. Okay, and the right hand side is equal to 0, right? The inner product of the 0 vector and any vector is equal to 0. We already proved that. Okay, and for the left hand side, we use the property of the inner product. I mean, use the axiom of the inner product that inner product can be distributed to each term, and you can pull and you can pull the constant out of the inner product. Okay, so we obtain this one. Okay, so we obtain this equation, and because the S is the orthogonal set, so if I is not equal to, so the inner product of VII is the norm of VI, right? And for the outer term is equal to 0, right? So this one, so the first term equal to 0 and blah 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 to last term is equal to 0. So we only have this term is the Ci multiplied with the inner product of VII. Okay, and equal to 0, and because Vi is not the 0 vector, then we can conclude that Ci is equal to 0 for all I in the set of 1 to n. Okay, so what does it mean? It means that S is linearly dependent. Okay. From this theorem, so from this theorem, you need to you need to do the inner product like this, right? So because before we move to the next slide, so you need to understand how to take the inner product. Okay. Okay, if you need to copy this page, so please pause it. Okay, next we will move to the next example. So the next example is I think is very easy. So, okay, but before we go to the next example, so we are talking about the definition of the orthonormal basis and orthogonal basis. Okay, what does it mean? It means that the orthogonal basis is the basis such that orthonormal, and the orthogonal basis is the basis such that orthogonal. Okay, orthonormal basis is the basis that orthonormal. What does it mean? It means that basis is an orthonormal set, and orthogonal basis is the basis that orthogonal. Okay. So this is the definition for the orthonormal and orthogonal basis. Okay. So we will move to the next example. So this one is very easy. So we know that the set of E1 to the En right here. So we know that this set, the set of E1 to En, is the standard basis for Rn, right? And if we use the Euclidean inner product, okay, if we use Euclidean inner product, you can see that if we calculate the inner product of Ei and Ej, so we have two cases. The first one is equal to 1 if I equal to j, and the second one is equal to 0 if I is not equal to j. So this one is, this one hold for I and j are elements in 1 to n, the set of 1 to n, right? Okay, so So we can conclude that this basis is orthogonal, is orthonormal, right? It's orthonormal. Why? Why is orthonormal? Because because of this one. So you can see that if I and j are equal, so the inner product of ei and ei is 1, and it's not then if I and j are not equal, then the inner product of I and j equal to 0. Okay, so the set of E1 to En is an orthonormal basis for Rn. Okay, next we will need to write. Okay, we need to write the solution. Okay, to show that the set of the standard basis of the Pn is an orthonormal with respect to the standard inner product. Okay, before we start, so we need to so we recall that the standard basis for Pn is the set of this one, right? It's 1 x squared blah 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 to the x to the power n, right? This one is the standard basis for Pn. Okay, and next, because we need to use the inner product, and this example say that we will use the standard inner product for Pn. So what is the standard inner product for Pn? Okay, the standard inner product for Pn is the if we let P be this a0 a1x blah 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 to the anx to the power n, and q is b0 plus b1x blah 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 to bnx here. So we define the inner product of p and q is the sum of the product of the coefficient, okay, from I equal to 1 equal to 0 to n. Okay, so you can see that this one is the product of the coefficient, right? That the coefficient of x to the power I. Okay, and when we find the product of the coefficient to x to the power I for all I, and we sum up. Okay, so we already showed that this one is the inner product. Okay, and this one is very easy. Why? Because for 1, okay, 1 is the one. What does it mean, 1? 1 is the polynomial, right? It's the constant polynomial. So we can show that. So it means that 1 is a 1 plus 1, and 0 times 1 times 1 plus 0 times x blah 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 to 0 times x to the power n. And for x is 0 times 1 plus 1 times x blah 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 to 0 times x to the power n. And the last one, x to the power n, is the 0 times 1 plus 0 times x blah 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 to 1 times x to the power n. Okay, so from this one it mean the coefficient of 1, the polynomial 1 is the coefficient of this one, the polynomial 1, the coefficient of 1, okay, is equal to 1, and coefficient of the x of this polynomial is 0. Okay, so we will use this form to find the value of the inner product. Okay, so it's not hard to find it. Okay, so we can see that if we calculate the inner product of x to the power I and x to the power j, you can see that if I is not equal to j, uh, the coefficient of x to the power I and x to the power a, and x to the power j are not same, right? So for this one, the coefficient is 1 and another one is 0. So the 1 times 0 is equal to 0. And this one is 0 and 1. 0 times 1 is 0. Okay? So the result is 0. Okay? And if I equal to j, so is equal to 1, right? And from this one from this one we can show that this set is autonomous basis. Okay. If you need to copy this page, so please pause it. And next we will move to some example. This example is the example from Rn. Okay, so we know that, so we already showed that the U1, U2, and U3 form an autonomous set, right? With respect to the Euclidean inner product on R3. And because we know that the set of U1, U2, and U3 is autonomous, right? So this implies that the set of U1, U2, and U3 is linearly dependent. And moreover, you know that the dimension of R3 is equal to 3. So what does it mean? It means that this set is a basis, right? It's a basis for Rn. And this set is autonomous set. So we can conclude that this set, the set of U1, U2, and U3 is an autonomous basis for R3. Okay. Okay, we will move to some theorem. Okay, so the question is, if we know or we can find the orthogonal basis, so what is the benefit from that basis? So the benefit is you can find the coefficient or you can find the coordinate of the vector like this. So we know that if normally we know that if S is if S is a basis, it's not autonomous basis. Okay. What does it mean? It means that for every v, if we have vector u, if we have a vector u in the span set of u1 to un, so from this one we know that u is c1 v1, u is equal to c1 u1 plus blah 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 to cn un. But so you just only know that c1 to cn are constant or are scalars, but we don't know about the value. We don't know about the explicit formula for c1 to cn, right? But if S, if the basis, this basis is orthogonal basis, so we can find the coefficient of u1 and blah 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 to coefficient of un. Okay, so this is our theorem. So we can show that if S is is an orthogonal basis, okay, for an inner product space V, and U is any vector in V, then U is equal to the linear combination of V1 to Vn by U equal to the inner product of U and V1 divided by the norm of V1 square times V1 plus blah 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 to the inner product of U and Vn divided by the norm of Vn square times Vn. Okay, and the second one, if S is an autonomous basis, then we can reduce our formula we can reduce our formula like here, like this. Okay, why we can reduce that? Because if this set is orthonormal basis, then the norm of each vector is equal to 1. So that's why we don't need to have the norm of square, okay, because of the norm of square is equal to 1. Okay, so from this theorem we suffice to show that number one's number one's whole. Okay, so how to prove the proof is very easy. It's not hard. So it look like how to find the C1 to Cn. Okay, so this is our proof. Okay, so we assume that S is orthogonal set. What does it mean? It means that the inner product of the V1 and Vi and Vj equal to 0 for all I and j, and I is not equal to j. Okay, and we let V be the vector in vector space V. Okay, and since we assume that S is a basis for V, then what does it mean? It means that there exists a scalar C1 to Cn such that V equal to C1 V1 plus blah 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 to Cn Vn like this. Okay, so how to calculate how to find C1, how to find the coefficient of this vector? So it's very easy. So we will use the inner product again. Okay, by we take the inner product with Vi. Okay, from the left hand side or right hand side, you can do that. Okay, so for the left hand side, so this one is equal to is the inner product of V and Vi, and the right hand side is the inner product of the sum of the C1 V1 to Cn Vn and Vi, and the left hand side we will use the properties of the inner product. Okay, we can distribute each inner product to each term, and we pull the scalar out from the inner product. Okay, and we obtain this formula, right? And from this one, because we know that S is an orthonormal set, what does it mean? It means that if I is not equal to I, I mean if I is not equal to I, so it's equal to 0, right? And we have only this term. Okay, the term of Ci is equal to the norm of it's not the norm. The Ci multiplied with the inner product of Vi and Vi. Okay, and we know that the inner product of Vi is the the norm of Vi square. Okay, so since the orthogonal set is not contain the 0 vector, okay, then we can show that Ci is equal to the inner product of V and Vi over the norm of Vi square. So this one is true for AVI. Okay, so that's why we obtain this formula. Okay, and for number two we use number one. Okay, so I don't need to discuss it again. Okay, so you can you can read it. Okay, so if you need to copy this slide, so please pause it. Okay,